Hi everyone! Today let's talk about session 4.6, the Poisson approximation to the binomial distribution. A random variable x has the Poisson distribution with parameter lambda greater or equal to 0 if the range of x is 0, 1, 2, etc. With the probability mass function is the following: f of k semicolons lambda equals p of x equals k equals e to the minus lambda times lambda to the k over k factorial. And we denote x has the Poisson distribution with the parameter lambda. Okay, so a couple remarks. First, remember for factorial, the 0 to the 0 is defined to be 1. And also 0 factorial is defined to be 1. So this symbol means it's defined to be. Okay, we define it to be 1. And then in order to show this is a probability distribution, remember for Pmf, probability mass function, we need a function is greater or equal to 0. And we also need to add up, when we add up all the probability, that equals 1. Okay, now you can see this guy, so f of k semicolon lambda, this guy e to the minus lambda is greater or equal to 0 because this is just exponential function is decreasing, right? And lambda to the k is because lambda is greater or equal to 0, so lambda to the k is positive, and then the k factorial is also positive. So everything is positive, so we know this guy is greater or equal to 0, right? Actually, it's positive. Okay, and furthermore, when we add them up, what happens? So when we add up, so the k goes from 0 to infinity. Okay, when we add those up, let's see what happens. We get, so e to the minus lambda to the k over k factorial. This is the sum is about k, so it means e to the minus lambda is like a constant, so we can move it in front of the summation sign. So we have the sum k from 0 to infinity, and then we have lambda to the k over k factorial. If you can remember from calculus 2, this is the Taylor series for e to the lambda. Okay, so this is the Taylor series for e to the lambda, and this series converges to e to the lambda, and the interval of convergence is minus infinity to infinity. So that's why we can say this guy is e to the lambda, so e to the minus lambda times e to the lambda. This is just 1 because they cancel out. So we can see when we add up all the probability, we get 1. So this is in fact a Pmf, probability mass function. And we call x with this probability mass function has the Poisson distribution. Okay? And so this is the formula for the Pmf. And we also have the CDF values. So the CDF values, we use capital F and then K lambda. So we have CDF values in our table 2. So in your textbook, remember table 1 was the CDF values for the binomial distribution. So table, and remember the n, we have n up to 20, right? So n up to 20. Then table 2 is the CDF for the Poisson distributions. And Poisson distribution, we have the lambda is the parameter. Okay, so you look at the lambda values. So these are the lambda values, and then we have the x values there. And I want to mention this, so you can see as we increase the lambda values, the x values also increasing. And notice that this page x only cover from 0 to 9, and so the next page you can see x cover it's greater than 9. Okay, so it's like it's one table, but it splits into 2 pages. So that's why sometimes when students, for example, they're looking for lambda equals 8 and x equals 11, and they realize, oh, why the table only cover 9? No, it's next page. So when lambda equals 8, right here, and x equals 11, so write this number. Okay, so when you read this table, you have to be careful. You might need to find different pages, okay, for the same lambda value. All right, very good. So let's continue. Okay, so because we have the CDF, so when you see the Poisson distribution, I suggest you to use the CDF values to compute. So CDF values, then you just find, remember, when you want to find the probability, you can use the CDF values, and you just pick 2 values, and then you just subtract them. Okay, so we will do some examples later today. Okay, fact. If x has the Poisson distribution, then the mean is lambda, and the variance is lambda. Well, here's the proof. So we're not going to go over the proof, but this is very easy to remember, right? Poisson distribution parameter is lambda, mean and variance are the same, lambda. Okay, so that's the fact. By the way, for all the distribution we learned, the formula for the mean and variance will be provided in the exam, so you don't have to memorize. Okay, you just need to figure out what kinds of the distribution and then use the correct formula to compute. Next, theorem, law of where event. Okay, if lambda is greater or equal to 0, Sn, let Sn be the binomial distribution with n is the number of trials. And let's say P, the probability of success is lambda over n. Okay, for all n greater or equals to lambda. Then the limits when n goes to infinity. So here we have the probability of Sn equals to k equals to, so this is the Poisson, the Pmf for the Poisson distribution. So this means when k is large, we can use the Poisson distribution to approximate the binomial distribution. Okay, so here you can see lambda is fixed, and when n goes to infinity, then p is lambda over n. So because our numerator is fixed, our denominator is getting bigger. So that's why the p is getting smaller. So p is very small. That's why this is called law of where event, because the probability of success is small. Okay, so in this case, we can use Poisson distribution to approximate the binomial distribution. Okay, so this is the theorem of law of where events. Okay. Alright, so let me show you the proof. Okay, so the probability of Sn equals k. So this is the Pmf for the binomial distribution. So we have a formula for it. So this is, we have n success, and we have k success in n trials. So that's why we have n choose k. And because we have k success, so the probability of success is p, so p to the k, and we have the probability of failure is 1 minus p, and we have n minus k failures. Okay, but what is p? P is lambda over n. So we plug in lambda over n. Okay, what is n choose k? Well, n choose k, this is combination. So this is n factorial over k factorial n minus k factorial. Okay, and then I'm gonna split this. So this is lambda to the k over n to the k. Alright, and then next guy, what I'm gonna to do is I rewrite this as 1 minus lambda over n to the, okay, so here what I'm gonna do is I'm gonna rewrite this as n over lambda times n minus k over n times lambda. Why can I do that? Oh, because you see, when we multiply them, n cancel, lambda cancel, and then we just get n minus k. So that's why I'm not changing it. This is still the same power. And just rewrite it like this. Okay? So now I'm gonna continue. So what I'm gonna do is look at these guys. Okay, what is this guy? So what is this guy? This guy is the same as n times n minus 1 times the dot times n minus k plus 1. Okay, and I want to put n to the k right here. So I want to put n. So there are k copies of n. Okay, and then what's next? I have lambda to the k, and we have the k factorial. I want to put the k factorial right here. For the next guy, I have 1 minus lambda over n. Okay, what I'm gonna do, I'm gonna split the power. So I want to rewrite this as negative n over lambda to the negative n minus k over n times lambda. And why I can do that? Well, that is because x to the a to the b is just x to the a times b, right? That's why I can move them. And here minus multiplied together, it just becomes positive. Okay, so now what happened? Keep in mind, when n goes to infinity, okay, so let's see. So n over n, this is just 1, right? And then n minus 1 over n, this is just like 1 minus 1 over n. Okay? And then times 1 minus 2 over n times the dot. This guy is 1 minus k minus 1 over n. So far, so good, everyone. And then we have the lambda to the k over k factorial. And we still have this guy 1 minus lambda over n to the minus n over lambda. And this guy to the minus n minus k over n times lambda. Okay, now let's let n goes to infinity and see what happens. So when n goes to infinity, this guy goes to 0. This guy goes to 0. This guy goes to 0. So 1 minus 0 is just 1. So this whole thing just goes to 1. Right? And what is this guy? This guy is actually goes to y. Okay, if you can remember the definitions of the number e, this is e. Okay, and then here when n goes to infinity, this guy just goes to minus lambda. Okay, so that's why when n goes to infinity, we just get 1, and then this is lambda to the k over k factorial times e to the minus lambda. Well, this is exactly the Pmf for the Poisson distribution. Right, so this is f of k semicolon lambda. This is the PMF of the Poisson distribution. So now we have shown that when n goes to infinity, the Poisson distribution can approximate the binomial distribution. Okay, so couple remark. So first remark, what is the mean of the binomial distribution? Well, this is n times p, but p in this case is lambda over n. And then you can see n cancel, we just get lambda. Wow, this match of the mean of our Poisson distribution. Right? And how about the variance? The variance of Sn is n times p times 1 minus p. So n times lambda over n times 1 minus lambda over n. Okay, this cancel, but you can see this is lambda times 1 minus lambda over n. But when n goes to infinity, lambda over n just goes to 0. So 1 minus 0 is 1. So this just converts to lambda. And lambda is exactly the variance of the Poisson distribution. So because we use the Poisson distribution to approximate the binomial distribution when n is large, so the mean and the variance should better match, right, when n is big. Okay? So second remark, if Sn has the binomial distribution and x, let's say x has the Poisson distribution, then we have the binomial distribution converge to the Poisson distribution when n goes to infinity. And this is convergence in, so this is convergence in distribution. Okay? And that is, so the binomial distribution is well approximated by the Poisson distribution when n is large. And the probability p equals lambda over n is small. Okay, so that's why success is where. So this is the law of where events, because the probability of success is small. Okay? And later on in chapter 5, when we introduce the normal distribution, and we will talk about when the n is large and the probability of success is not small, which is like close to 0.5, then we can actually use the normal distribution to approximate the binomial distribution. So we'll talk about that in chapter 5. So for now, just keep in mind, if n is large and p is small, then we can use the Poisson distribution to approximate the binomial distribution. All right, let's look at example 1. 5% of the books bound at a certain bindery have defective bindings. Find the probability 2 of 100 books have defective bindings through Part A, binomial distribution. Part B, Poisson approximation. Okay, so Part A, 5% of the books. So P is, let's say, 2 out of 100. So K is 2, and number of trials is 100, and then probability of success 5%, so which is 0.05. And remember, we have two ways to compute the binomial distributions. Either use the Pmf, which is a formula, or we can use the CDF. But the CDF table, okay, so CDF table for the binomial distributions only cover the n up to 20. So in this problem, n is 100. So we cannot use the table, the CDF table, to compute. Okay, so we have B, and then K is 2, N is 100, P is 0.05. So what is this? Well, we have 100 books, and we pick 2 out of it, and the probability of success 0.05. We have 2 success, the probability of failure is 0.95, and we have 98 failures. And 100 choose 2 is 100. 99 we count down for 2 numbers, divided by 2 times 1. Okay, and then we have 0.05 squared, 0.95, 98. And what is this number? Okay, calculator. Let's see. Okay, let me move this up a little bit. Okay, so we get 100 times 99 divided by 2, and then times 0.05 squared times 0.95 to the 98. Okay, so we get 0.08118. Oops, sorry. It's so sensitive. 0.0 and then what? 8118. Okay, so this is part A. Alright, part B, use the Poisson approximation. So Poisson approximation, here K is again 2, but then what is lambda? Okay, remember P, because P equals lambda over N, then lambda equals N times P. Okay, N is 100, P is 0.05, so that's why it's 5. Okay, so the probability x equals 2. So there are 2 ways to compute the Poisson distribution. One is using the Pmf. The other way is use the CDF, which is the table 2. So I'm going to do both ways with you. Okay, so method 1, we can use the Pmf. So what is the Pmf formula? Well, that is e to the minus lambda times lambda to the k over k factorial. Okay, and we plug in k equals to 2 and lambda equals 5. So e to the minus 5, 5 to the k is 2 over 2 factorial, which is 2. What is this number? So we have e to the minus 5. Oops. And then times 5 squared, which is 25, divided by 2. So we get 0.08422. 0.08422. Okay, now you can see it kind of close. Okay, so this is method 1. Method 2 is use the CDF to compute. Okay, so P x equals 2. Well, remember, how do you compute x equals 2? Well, that's x less than equal to 2 minus x less than equal to 1, right? So that is f of 2, lambda is 5, minus f of 1, lambda is 5. And then this is, we use the CDF to compute, and we're in table 2. So table 2, this is the table 2. And we're looking for the then lambda equals 5. So this lambda equals 5. And when k is 2, 0.125. 0.125 minus 0.04. 0.04. And what is that? Okay, so now you can see 0.125 minus 0.04. The answer is 0.085. And you can see the number, they are still close. Okay? And in general, I suggest you use the CDF values to compute. Use the CDF values, you just simply find the two number from the table and you do subtraction. Well, if you use the Pmf value, well then the calculation will be more complicated. It involves powers, divisions, factorial, etc. Okay, so that's why for binomial distribution and Poisson distribution, I suggest you to use the CDF values. So table 1 for the binomial distribution and table 2 for the Poisson distribution to compute. So far, so good, everyone. Okay, so let's continue in the next video. See you soon.